Okay, we are ready. Hello, my name is Daniel. I'm the Technical Customer Success Manager of WinDriver. If you already subscribed to WinDriver, so we've probably talked before. I will present the DMA webinar for today. I guess 6 months ago, we hosted a webinar. We called it DMA 101, Theory and Practice. This one has a few significant changes, both in content and in structure. So let's begin. I just want to note the chat is open. I can read your comments. If you have any question or any comment, you can send it to me via the chat, and I will look into it. So this is the second webinar from 4 webinars. We are hosting a series of 4 webinars. 2 weeks ago, we hosted the WinDriver introduction webinar, which is already on YouTube. And in 2 weeks, we will host a webinar introducing WinDriver's new version 16.4 features, including lattice DMA IP samples for Avant and CPNX devices. I will talk about it later. And a new model for managing licenses. Very exciting feature that takes WinDriver one step or even a few steps towards being a SaaS solution. And we will host another interrupt handler or PCIe diag webinar. We hosted one before, and you can find it on YouTube. But again, this will be changed and modified and enhanced on March 17th. I highly recommend following us on LinkedIn. We post content on a weekly basis, including the events, the webinars. All of them are free. So stay updated, follow us on LinkedIn, and stay tuned regarding our content and events. In addition to these events, we also have some very interesting blog posts, webinars we've recorded before, like debugging webinar, and tutorials on our website. So if you don't know the address, look for a WinDriver, Django WinDriver on Google, and you'll get there, and you can find a lot of interesting content there. So what are we going to do today? We'll start with the fun part. We'll start with the live demonstrations. I must say, these are all available on the free trial version of WinDriver. So if you haven't downloaded WinDriver and you will download it, you will have access to everything I'm just about to show. And about 90% of the features I will present now are available for a regular subscription. So if you have a license or if you're on your free trial period, you can make it a hands-on webinar and do as I do and see how easy it is to do everything we are about to do. We will cover DMA definitions. So if I am saying things or using terms that you do not understand during the demo, don't worry. I will cover everything in the definitions part. I assume that most of you are familiar with DMA or what it is, and if not, then this would be your chapter of this webinar where I'll explain everything. The third part is very technical, and in this part we will see how What is the best practice for implementing direct memory access as per WinDriver? We will deep dive into specific functions, the XDMA code, and we will see what is the recommended routine by us to implement an effective DMA. The last part, everything that that couldn't be included in all the other chapters, DMA extras, where I will talk about debugging. I will talk about how to pre-allocate DMA buffer on Windows and the special APIs allowing to send DMA to allocate a DMA buffer and share it with other processes, which can make the performance significantly faster if you want to share the data from your DMA with other processes. A few more notes. So as I said, WinDriver is available for download and it is free for 30 days on Windows and 60 minutes on Linux. If you haven't tried that, do it now. Go to our website and download WinDriver and install it. It's very easy. Almost everything I will show this in this webinar has cross-platform functionality, which means you can build it, run it, and use it in Linux as well. ARM is rising, the usage in ARM processors. WinDriver is ARM compatible. We have dedicated ARM libraries. So again, a huge advantage if you're using ARM or also ARM, you can do what we are doing here, and it will be compatible. Implementing DMA is hard without WinDriver. Developing drivers is hard without WinDriver. We offer support. We offer a lot of content and an elaborated documentation, which we will see today on everything, on every step. So you can succeed in your goal, developing efficient drivers easily. So you will see me go through Windows today. I recommend you to do the same. Explore all of our supporting options, and you can find a lot of relevant information there. 2 things we will launch soon. As I said, we partnered with Lattice. We have DMA IP samples for CPNX and Avant. If you're not sure what DMA IP samples are, I will talk about it shortly. But we will have the same as we have for Xilinx. For Xilinx, we will have for Lattice as well. Another feature our R&D team is working on is the option to implement a kernel plugin in a DMA. A kernel plugin is a chunk of code that is being transferred to the kernel mode, which eliminates the context switch and hence is faster. So if DMA is supposed to make your performance faster, kernel plugin with DMA is a game changer as well. You can also implement an interrupt handler inside the kernel plugin and immediately raise an interrupt from the kernel, which is a huge advantage. So that's it for that. Let's start. Okay, live demo. What are we going to do today? We will see how we can allocate a DMA buffer without generating any code. And I'm going from the easiest to, I don't want to say the hardest because there is no hard in this, but to the more complicated in terms of process. So we will start by allocating a DMA buffer without generating any code. Then we will open the XDMA sample. I will talk about what are samples, dive into the sample, not too deeply, and then generate a DMA code via the wizard. Since I don't have a DMA compatible device on my computer, I will show you a video demonstrating how a DMA application looks like and how it transfers looks like. It's very straightforward, and it is available on your YouTube. So if you want to look into it too, you can find it on our YouTube page. Let's start. So I will open WinDriver's folder. I know that's small. Okay. This is WinDriver's folder. And in this folder, we can find several folders. One of them is the samples folder. The samples folder contain sample codes with specific functionalities in different languages. Okay, so we have .NET, Python, PowerShell, Java, and the C#.NET, Visual Basic, of course. And we will work with C today, but you can work with other languages. And here we have several samples. So we have sample codes for Altera, XDMA IP, Lattice, and we will add to that soon. Xilinx. And the one I will choose now is the PCI Diag, PCI Diagnostic App. What's in it? So the PCI Diagnostic App is an application that you don't really need to build. If you install WinDriver, okay, here I have it. Sorry, you may need to build it to compile it, and if you change your license, you need to update the license in this utility as well. I hope you can see that clearly. Okay, I think that's big enough. So this is a utility that allows me to open my devices and access them just like that. If I have an INF installed on my device, I can open it and do many things with it. So I want to ask for the PCI Diag to scan all my devices. Okay, so here I have a list. And I see the vendor ID, the VITPID, the location, the interrupts available, the memory range, and so on, of all my PCI devices on my machine. I would like to choose this device. Okay, and here I have it. I haven't done anything, no code, nothing, and I already have an access to my device. So I can do a few things. I can allocate or free a shared buffer, manage IPC. We have a webinar dedicated for it. I won't get into it now. Read or write to the PCI configuration space. And you see, there are several things we can do here. The webinar 1 month from now, on March 17th, will be dedicated for this tool, for the PCI Diag and the interrupt handler it includes. What I want here, I want to show you is how to allocate or free a memory for DMA, because the DMA is our thing now. Let's choose this option. And I can choose whether to allocate a contiguous memory or a scatter gather memory. I will talk about the differences between them later if you're not sure what's the difference. But let's go with scatter-gather because it's harder to implement. I can choose the memory size. So I will choose a big size, a large one, because I wanted to be challenging to fill a contiguous memory with that size. And here I have it. Scatter-gather memory allocated. I have the user address, I have the size, and I have the pages. And you can see the address of each page and the size of each page. So without doing almost nothing, clicking a few numbers, no coding, nothing complicated, I have an allocated DMA buffers, okay, on my PC. So it's just to show you the ease of use. The PCIe DAG utility does not have more advanced DMA features. For this purpose, we will open the XDMA DAG tool. Let's just free the memory again with the push of a button. And here we have it. The DMA memory is freed. Let's close this application. And open, let's go back to samples, see the Xilinx XDMA. I would want to open this sample with Visual Studio, with Visual Studio, so we can look further into the code. Okay, here I have it. I will demonstrate how to open a new project next. After I will generate the code via the wizard. I will explain about CMake. So we have the XDMA lib.c, which is the logic of our application. You can see, and again, I haven't generated nothing. It exists on my sample folder. We have the libraries initialization. We have the device open and close functions. All the structs that are required. We have the interrupt structs, functions and structs, and we demonstrate here how it can be implemented. Okay, the interrupt handler, how to enable interrupt, how to disable the interrupts. And what's special in the XDMA sample is that we created it based on Xilinx specific devices, okay, Stratix and Cyclone 10. And in this each device is unique. It has its own parameters and definitions and offsets, and you must know what to write where and what to read from where in order for things to work properly and not damaging the card. So the devices our team, R&D team, worked on configurations are already implemented in the XDMA sample. You can see, okay, that we have fields here that store device-specific information, and you can add it there. So if you open Stratix 10 manual, you will see these parameters, okay, and these specific offsets or bytes are corresponding with the manual. So everything is here was implemented already by our R&D team. Again, for your convenience, if you are using a different device or you want to add more fields, you can do so. just by adding it here. So this is the XDMA sample. I will run it now. And we see that I got an error. The reason that I got this error is because I don't have a DMA compatible device on this host. It won't prevent me from scanning the devices. However, it won't let me open one because it won't be able to identify the config bar required to perform the DMA operations. But if you have a DMA device on your machine, it should work. It should identify it, and you can see the DMA menu, which we will see on the video just after generating the code. So this is the XDMA sample, a very important one. Why is it so important? It is on sample folder, C, Xilinx, XDMA. Why is it so important? You can access the application also here. Why is it so important? First of all, it should be your skeletal code for DMA applications because it is a working sample, and it's a great debugging tool because it is a working sample. So if the functions are working there, then and something is not working well with your application, then something must lost in the development process. So I don't recommend writing to unfamiliar offsets and memory segments with your device. However, open your device and see if it works, and allocate and lock memory segments and see that it is a working sample. Another way to create such a sample is to generate it from the wizard. If you are not familiar with WinDriver, you will have a chance now to see the wizard and how it works. Of course, it went to the other window. I won't go over everything because 2 weeks ago we had an introduction webinar where we covered all the wizard features, but I will talk about the DMA capabilities. So here you can pre-allocate a device to host or host to device DMA buffers. Generate an INF file. If you're not sure what INF is the key for your hardware on Windows. Without a device INF, no process or application will be able to access your device, and you can generate an INF with WinDriver, automatically generate it. Now, why do we need to pre-allocate DMA buffers? On Linux, we don't have such a problem where the operating system is too big or too strong to capture too much space. On Windows, however, we have such a risk, especially if we want large DMA buffers. So you have the option to pre-allocate DMA buffers inside the INF, from the INF, choose the size, and it will allocate and lock the buffers from the boot, okay? It won't wait until all the programs have already taken most of the memories. It will capture it during the boot, ensuring the memory that you need in order to perform the DMA. I already have an INF for this device, so I'll click next. Let's call it alpha. Okay. Here I have the wizard, interrupt handler built in, a memory bar, can create access register, read and write. I covered most of it in last week's webinar. How do we generate a DMA sample code? And again, I'm doing it fairly fast, but it's also because it is very easy. Here in the device-specific customization, I can choose Xilinx XDMA design. We also have Altera Avalon memory mapped only design for Stratix 10 and Cyclone 10, and BMD, QDMA, and XDMA designs IP for Xilinx. You can choose this option here, and it will generate an XDMA sample to your code. I will do it just now. In the next version, we will also have Lattice samples option here. I'm always compiling with CMake. I'm not sure if you're familiar with CMake. It's a very convenient tool, a cross-platform build tool. We save you all the configurations required when wanting to build in different operating systems. CentOS, Windows, Linux, just one file to build in each one of them, and I will show you how it works now. So let's choose CMake. I can generate a separate library for only the application logic, the dynamic library to be implemented in another UI or in another application. And another option I have is to generate a kernel plugin. I won't get into it now, but as I said, we are planning to add the kernel plugin functionality to the DMA routine. That's it. I have my project ready. Let's open the folder. I want to close everything here. Why? Because if WinDriver will open my device and I will try to run the code, it will create a resource overlap error. So I'm getting a warning. Make sure to close WinDriver before running your application or executing your code. Click OK and close this window. Now every configuration I've added on the wizard is now available. I haven't done any configurations, but it should be available here on my code. Let's see how CMake works. Opening CMake. Alpha is my project. I'm opening it and giving it a few moments because it initializes it. Here we see. And everything is set. Okay, this is the CMake file. You can see that we have all the flags and definitions required here in order to complete the build successfully in every platform. Then I go to CMake targets view, alpha project, and here I have my files. Okay, all my files with all the definitions required for my application to work properly. I'm not changing anything. Maybe I'll need to change the license. Let's build it. And run. Okay. Here I have my application. Again, with almost no code or no complicated steps, I have my application working. I will enter the license now in order to get this error message to disappear and show you that it is working as expected. So in lib.c, I can edit my license string, and if I'm changing the driver name from WinDriver, distributing my driver, I would change the WD default driver name base struct to my kernel module. Let's build it again. Run this application. And here we have it. It's not invalid license. It's the failed to open a PCI device because, again, I don't have DMA compatible device on my host currently. So we saw how to generate an XDMA sample from the wizard. If you have any questions, again, write me on chat. Now we will see the video demonstrating or showcasing how the DMA application looks like. Okay. Just a second. Okay. So this video is part of WinDriver Quick, a series of tutorials. We are keep adding. Okay. So this demonstration took place on Linux. We open the WD debug. I will talk about it. Okay. And when I'm opening the, sorry. When I'm opening my device or my application, sorry for disappearing. So when I'm opening my application, okay, this is what it looks like. We have an XDMA DMA menu. I can perform the DMA transfer or measure it. I'm choosing, just a second, performing the DMA. Sorry for the mess. Okay, here I'm opening the XDMA diag, the application we're using now. In my options, I can find and open an XDMA device. I'm choosing option 2 and entering the VTPID of my device. And then I get this XDMA main menu. I can perform several operations here, but I choose direct memory access, option number 6. After choosing option number 6, I can either perform the DMA transfer or measure it. If I choose to perform, I need to choose open DMA, which is a specific function we will cover. Select the DMA completion method, interrupts or polling. I will talk about this as well. And select the DMA direction from device or to device. Okay, exactly what we're covering here. And then we get to the technical details of the transfer. We choose the channel. Don't choose 0 by default. It depends on your device. Enter the data pattern. So this is the data I want to be transferred. Enter the number of packets. I want 4 packets of this data. And the offset for the transfer, which is critical. You must know the offset of your device in order to ensure that it gets to the right place. Okay. And we can see that this message triggered an interrupt. We see that the message signaled interrupt number 1 received. We have the DMA status and the interrupt status, and that the DMA transfer is complete. So this is how it looks like. After you configure your DMA parameters and program, you will have a menu, a DMA menu, where you can execute and perform the DMA from your device. This is just one way to perform the DMA, but this is the options we provide with the XDMA sample with DMA compatible devices. Okay, here I'm doing it again. Sorry, I've closed the DMA. and the interrupt handler was disabled automatically, and I will cover it shortly. So this is what I wanted to show. I'm sorry it's not a live webinar, it's not a live demo. However, it should give you a clue for how it looks like a DMA menu in a user app. So after demonstrating things in the practical level, what to click where and where to find what, let's go over a few definitions. I hope it will make things clearer than if things were not understood so far. So what is the DMA? DMA is a mechanism where data is transferred between devices without involving the CPU directly. Okay, so here we have the CPU. In regular cases, the communication goes through the CPU to take requests, to manage power events, and so on. In DMA, we create a direct channel between the PCIe device and the memory component, mostly RAM, but it can also be a ROM, a hard drive. And via the DMA controller, you can create data transfers without involving the CPU. There is another component called IOMMU. I won't elaborate too much about it, but we have an interesting research I will talk about shortly. So we said this is DMA, and there are different types and methods in order to perform DMA. So we said that we want to keep the CPU as much as we can out of the transfer, out of this operation, for both faster transfer and to reduce the occupancy of the CPU. Let's say the default or classic DMA method is polling. During polling, the CPU keeps asking the process or the driver, are you done? Are you done with the DMA? And if the answer is no, then it moves to the next iteration or next operation, and then it asks, are you done yet? And if the answer is no, and so on and so on. And basically, it's quite straightforward. The CPU keeps asking, are you done? No, are you done? No, until the answer is yes. And then the CPU knows that the DMA transfer has ended. It is both time and resources consuming for the CPU and the DMA process. So another option to perform this operation is with the interrupt method. So the PCIe and the RAM facilitate the connection with the locked buffers, and the program executes and all the memory is flowing. And when the transfer is done, an interrupt is raised using an interrupt handler, saying to the CPU, the transfer is done. So give us whatever you need to order, for us to continue or to synchronize other components within the computer. But it takes less resources. Harder to implement, but it takes less resources. So these are the two methods for conducting DMA. And there are also different DMA types. Okay, so blocking and non-blocking is the non-DMA ways to transfer data. There are DMA with interrupt method and polling method. The question, which is faster? So one may think that interrupt is usually faster. However, it is best to try both. I mean, if you can, each device and each operating system works differently. So one may work faster with this, and another work faster with the interrupt. Someone is asking, will I share my slides? I can. Send me your email and I will send it to you after the presentation. Okay, so we talked about how the CPU is involved in the DMA. And there is another question when you plan a DMA for how the memory buffer is looks like, or what kind of memory buffer do we want. So there are two types of memory buffer. One is contiguous, and the other one is scatter-gather. In contiguous DMA, we get a single segment of memory allocated, and all the memory is being written and deleted and so on here. In scatter-gather DMA, there are multiple non-contiguous blocks of memory allocated and locked. The advantages. So contiguous is more robust. Let's start from the top. Scatter-gather is more robust, okay? Because if we need a large buffer of DMA and we set it to be contiguous and this memory section is not available on our memory, then the DMA will fail. So contiguous is scatter-gather is more robust, contiguous is less robust. We saw that it easy enough to allocate a scatter-gather memory section. However, it might be more challenging to cope with or to manage it. So these are the main differences between scatter-gather and contiguous, and these are the again the visual representation of each DMA type and how it looks like. So we have contiguous and scatter-gather. I want to show you research made in our R&D team, by our R&D team, for comparing DMA performance. You can find it on our website, Media Blogs, and this is the headline. Basically, what they've done is taking the same architecture. Okay, we have the hardware and the operating system here. Trying different kernel versions, trying different interrupt types. Okay, whether it's polling or interrupt handler driven. Tried to work with the IOMMU component instead of the DMA controller, and got some interesting results. And tried it with ARM and non-ARM platforms. And we have a summary of the conclusions. I must say, it is a very, very, very specific outcome based on our specific devices and their specifications. What I want, if people want to get, I don't know, inspired or take from it, is to try themselves. For example, we saw that large buffers doesn't necessarily mean a faster DMA. Okay, there's an optimum point. After it, the performance diminishes. So we have the research here. If you're interested, we have two accompanying blogs regarding polling versus the interrupt, and scatter-gather and contiguous, elaborating on these types of DMA. So you can find it on our website. I don't want it to take too much time from us, from what's left. Let's talk about, we're now diving into the technical part, API types. WinDriver has two API types, a high-level API and low-level API. We recommend working only with high-level APIs. These are newer, more advanced, easier to work with, and perform more operation than the low-level APIs. Basically, the high-level API is managed from the user mode, and the low-level API sits in the kernel mode. For our cases, the the important functions are the WDC DMA scatter gather buff lock that locks scatter gather buffers. We have the same one for contiguous. We have the unlock buffer function and the interrupt handler functions for enabling and disabling. And now if I click on each of these, you can see that there is a documentation that really tells everything you need to know about the signature, the parameters, the values, and it also, you can also find it in the code. Okay. Generating a DMA code on the wizard, we've talked about it. It's a diagnostic program, a skeletal driver, device driver. We talked about makefile. I said we have samples for Altera, Xilinx, XDMA, QDMA. Okay, so let's talk about how to implement DMA. The sequence, as far as WinDriver goes, or what WinDriver does, is to allocate a user mode buffer, locking it, and notify or ends the DMA. Okay, this is what our API provides. To allocate the buffer, lock it, so other processes can't access it. In the middle, there is your program, okay? What you want to be transferred, what data, to which offsets, what do you want to happen? Do you want to enter, to add an interrupt handler or not? That all depends on you. But WinDriver gives you everything you need in order to perform in the buffer required to perform the DMA. Let's go over the routine. Okay, and in this case, let's do something like this. Here we have the routine. And I'll open XDMA right here. Okay. And we can see okay. So now we can see the functions. Okay, we have it side by side. I hope that's large enough for you to see. So this is the best practice we recommend for implementing DMA. So as I said, it starts from allocating, continues with locking, okay, and ends with closing. Let's go to scatter gather, which is considered more difficult to perform. So your DMA routine function, you add it, should include these parameters. Let's talk about the WDMA struct, which you can find also here. Okay, this is a critical struct because it includes all the necessary information about the DMA. Okay, handle for the buffer, user address, kernel address, the size of buffer, all the relevant information for your DMA is included here. We can find it on our code as well. Okay, this is the struct. And you can see it here, a handle, a user address, a kernel address, size of buffer, the alignment is here. If in a low-level API, you had to manually, or let's say you had a more complicated, more complex process with the alignment, here it is much more straightforward. Maximum transfer size, all the required element in order to perform the DMA. And again, almost everything we show here is available and exemplified in the XDMA diag. Okay, so we have the allocate of the user mode and then locking the DMA buffer to the DMA controller. Okay, it's not the locking in the memory. So if we want to see how this was implemented with these parameters, we can find it here, okay, on our XDMA code. Again, it's the XDMA sample. You don't need to generate anything. To open a DMA handle, allocating and initialize XDMA DMA information structure, including allocation of scatter-gather DMA buffer. Okay, so this is how it looks like. This is the function. You can see the logs that are relevant, the error logs, and all the relevant information required in order to implement a successful DMA opening. Now, remember when we talked about interrupts, we said that there is polling method and interrupt method. In this part, you should indicate or define which type are you using, whether it's polling or interrupt method. Again, here we have the sample for it. We have the XDMA int enable with all the relevant functions and parameters needed to enable interrupts. Okay, we have all the structs that are required exemplified here. This is a working sample. This part is critical. Flushing the CPU cache before starting the DMA and flushing it afterwards, because there may be some data that was in this buffer, if it's from your driver or other processes, and even corrupted data within or between DMA transfers. So we really recommend getting familiar with these functions, the DMA sync CPU and the DMA sync IO, that really keeps the buffer clean. It's clickable. Okay, you can see here the definitions. And utilize it in order to prevent data corruption. Let's continue. My DMA start is your program. Okay, what do you want? What do you want happening after the we have the buffer locked, allocated, and locked? And DMA close again is closing everything, freeing the buffers and disabling the interrupt handler. Let's see how we've implemented the DMA open function. Okay, so here you can see that open a DMA handle, allocate and initialize the XDMA information struct. You can choose the direction, lock a scatter gather DMA buffer with the DMA scatter gather buff lock. That happens quite automatically, as you saw. Of course, it threw me. Okay. And this is, and eventually, just to see I'm not missing anything, getting to the DMA close, again, disabling the DMA interrupts if enabled. So if you're not familiar with it, this is the way we recommend implementing your DMA program. And you can see how we created our sample and rely on it. Moreover, we recommend taking the XDMA sample and build your code on top of it, because this routine is already configured and implemented there. Sorry, okay. Why doesn't it let me? When I talked about offsets and device specifics this is what I've talked about. Each device comes with the manual and product specifications. In this case, it's a Xilinx product specification page with a descriptive format. It includes the fields, the bit index, the description, and everything. So before even trying to plan and see what your driver is aimed to do, be familiar with your device and make sure you understand which offset does what and which functionality is open. So there are a few things that we haven't implemented. The first one is, as I said, the DMA start that says, tells to the device, initiate the DMA transfer. The DMA wait for completion is if you're using polling. Remember when we saw that scheme? So the waiting for completion is when the answer is no. Either continue, poll the device for completion, or wait for DMA done interrupt. If you're not using polling method, then you need to use an interrupt handler, which we also provide, if I haven't showed that. Here we have the XDMA int enable. I already showed it, okay. With all the relevant functions in order to have a built-in interrupt handler for your DMA program, and the DMA int handler, okay, the device's interrupt handler, a pointer to a function prototype of your choice. The DMA close, I think it's pretty straightforward. Let's talk about some extras and we'll wrap it up. Debugging. So WinDriver comes with a built-in debugger. It's called the WD debug. You can access it via the here. WinDriver, util folder, WD debug. Okay, we're opening it. It captured everything I just did. Let's close it. Pretty quick. Let's run it. Okay, I'm running my application. And based on my kernel module, it monitors all the operations, kernel operations that are taking place. You can see all the relevant functions, failures and errors in red, and we know this error was expected, but we really recommend using the debugger, WinDriver's debugger, built-in debugger. How a DMA looks like in the debugger. So DMA contain alloc. We said we're allocating, we are locking and freeing. Okay, so you can see it's the same address, right? We have success logs, and it makes the whole troubleshooting much easier, especially when we're talking about complicated things like DMA. If you encounter issues, you can't understand what went wrong with your application, and you need assistance in figuring out the logs, contact us. We eat this for breakfast. A shared DMA buffer. I said I will talk about it. It's a special API. It is included in the free trial, but if you will purchase a license, you will need to buy it additionally, with additional cost. I mean, in this scheme, we can see that there is an input. It's just a use case, but the concept is the same. The PCIe does something, sends a DMA output to the RAM memory. Now, let's say that we want a USB device, a graphic card, and a hard drive to access this data. And we want them to access it fast. We can create a locking mechanism, an access mechanism, and make sure that if this one access the buffer, then this one doesn't, and it's a complete headache. What we offer is to create a shared DMA buffer. This is a memory segment that broadcasts the data from this buffer to several processes. very, very convenient. So this is another very advanced capability and feature we offer, but it exists, and I recommend you being familiar with it. And the last one is the pre-allocation of buffer on Windows. As I said, if you have DMA capability, these fields will be available for you, and you can allocate buffers that will be captured during the boot. You can also do it by editing the INF manually, or changing the DMA config bufflock flag in the function. One last thing we recommend watching when performing DMA on Windows is that the kernel DMA protection is off. Okay, this is the system information application, because if it is on, you will get a blue screen. We saw several cases like that. And I want to thank you. I hope it was clear. I know that was a lot. If you have any questions or feedback, please send it to my email or the sales email. I will send the slide for the one who asked. If you want the slide, send me a message and I will send it to you. And I want to thank you for listening and taking your time.